In lecture, we saw that we can represent rotations as rotation matrices, Euler angles, and the axis angle representation. In this segment, we'll discuss a final method of representation for rotations, namely using quaternions. A quaternion is a four-tuple. This set of numbers is often interpreted as a constant component Q0 and a three-dimensional vector component Q. We can use this representation for defining common operations on quaternions. To add or subtract two quaternions P and Q, we simply add or subtract the corresponding components. Quaternion multiplication is defined by the following equation. The inverse of a quaternion is a quaternion where the constant component Q0 remains unchanged, but the vector component is negated. Quaternions can be used to represent rigid body rotations. In particular, we can easily convert an axis angle representation of a rotation to its quaternion representation. Recall that in the axis angle representation, we found an angle of rotation phi and an axis of rotation u. The equivalent quaternion in terms of these two parameters can be found using the following equation. Given a quaternion q, we can also find the equivalent axis angle representation. We can find the angle of rotation using the constant component q0. The axis of rotation is a function of all four components. How do we actually use these quaternions? Suppose we want to rotate a vector p in R3 by the quaternion q. To do this, we first turn the vector p into a quaternion that has 0 as a constant component and p as a vector component. To perform the rotation, we pre-multiply by q and post-multiply by q inverse. The resulting quaternion will still have 0 as its constant component. The vector component is the vector that results after rotating p. Here, we are taking the quaternion product. It is also easy to compose rotations in the quaternion representation. A rotation of q1 followed by a second rotation q2 is represented by the quaternion q equals q2 times q1, where again we are taking the quaternion product of q2 and q1. Like the axis angle representation, there are two quaternion representations for each rotation. Q and negative q represent the same rotation. There are a number of advantages to the quaternion representation. A quaternion only has four parameters, making it a more compact representation than rotation matrices. Furthermore, the quaternion representation contains no singularities. The quaternion product is also often more numerically stable than matrix multiplication, making it a common choice when working with rotations in software.